Just beyond point 2. Yeah, remember? We complete the first sub-problems. Yeah. Let me move to the place. So we pretty much near the end of this slide. Yeah. Yeah. So what we are doing here, our goal, we want to solve. Let me put my presentation machine on the stand. All right. All right, yeah, looks good. Yeah. So currently, our goal, we want to solve this problem. Evaluate a given polynomial, arbitrary given polynomial, efficiently. Yeah. So this problem we treat, relatively hard. Yeah. So usually, for a relatively hard computing problem, in order to solve it, we use divide and conquer approach. Divide and conquer approach. Yeah. So we divide that relatively hard problem into several smaller subproblems. Our first subproblem, count the number of additions, because we know we need to use additions, multiplications to find the value of this polynomial. So the first subproblem, count the number of additions used by our current method. What is our current method? Our current method is brute force method. Okay? Brute force, straightforward method. We didn't use any special technique. Yeah, we just, do it directly. So by the brute force method, the number of additions used to do the calculation and additions. That's what we did last time. Then we move to the second subproblem. We need to count the number of multiplications. Okay? Yeah, second subproblem. All right, but we did partially last time already. So this time, let's complete the second subproblem. All right, yeah. So subproblem number 2. Count the number of multiplications. Let's do the work. Last time, remember, we did a counting for a general term. Okay? General term, ak times x to the kth power. Yeah. That expression, we have that partial result, right? Yeah. So let's continue. Yeah, let's use this partial result and complete the remaining counting work. Yeah. All right. So then, this time, we need to accumulate a number of multiplications for all the terms. We have n plus 1 terms. Yeah. Yeah. Let's do the counting. Okay? All right. Yeah. But the first term, we know the first term does not contribute any multiplication, right? 0 multiplication. No contribution. Okay? So when we do the accumulation, we start from the second term. Okay? All right. So let us add up. Yeah, here I do a chart. Add up all the number of multiplication. The second term, contribution, 1 multiplication. Third term, 2 multiplications, and so on. The last term, n multiplications. Let's add them. Add them up. Yeah. Add up all these numbers to get a total. Yeah. So the total number of multiplication, do you remember the formula for this one? From your discrete math? The summation of the first n consecutive positive integers. Is there some nice formula? Simple, nice formula? You can, have some impression? Yeah. Yeah. Let me give you the answer. 1/2 times n plus 1. 1/2 times m times n plus 1. Yeah. Why is that? Yeah. So here, yeah, because for many people, they feel pretty hard to memorize formulas, right? So you have large number of formulas in math. How can a person memorize most of the important formulas, right? Some people feel not easy. Yeah. Here, if you have some, nice understanding in your mind, then very easy, because it's very natural. Yeah. Here, let me explain a special way to view this formula. Do you know how to calculate the area of a triangle? Do you know the formula calculating area of a triangle? Yeah, right. Yeah. Yeah. So that formula, I believe, most of the students in this class, know how to calculate area of a triangle. Here, let's use that on this formula. Okay. Yeah. Let me draw a triangle. This is my triangle. Okay? All right. Then, on this top, one dot I put on top. Then the next row, I put 2 dots. Okay? All right. Then, next row, 3 dots, and so on. Okay? Yeah. Yeah. Then the bottom row, n dots. All right? Okay. Now, in order to calculate the summation, so we add up all these dots, right? Let's apply the formula for the area of triangle. Okay? Yeah. 1/2 base number is n, right? Yeah. Top number, there is 1 there. What's the height? High number also n. Okay? All right. So 1/2 times height number n, base number plus the top number, right? Yeah. Corresponding to the area of a triangle. Yeah. Yeah. So strictly speaking, probably you want to say the area of the trapezoid. Yeah, because the top, there is 1 dot. Okay? For triangle, the length of the top is 0, right? Yeah. The length of the, but if you look at it as a trapezoid, okay? Yeah. So the length of the top is 1, not 0. Okay? Trapezoid. So the formula of a trapezoid. Okay? Yeah. Yeah. With that formula, yeah, you can memorize the summation formula easily. Okay? All right? Yeah. So we find the final answer. Yeah. All right. So we finish our second subproblem, counting the number of multiplications. Okay? All right? Yeah. Then, yeah, because remember, we need to recall, we have 2 types of operations: addition type, multiplication type. Yeah. Because we cannot compare apple and pear, 2 different objects. Yeah. In order to do some fair comparison, because we want to calculate the total number of certain units, yeah, for a fair measurement. Yeah. Remember, last time at the end, we used a reasonable assumption. Here, I don't want to go back to the previous slide. All right. I just describe it. Our previous assumption, that is, we assume the amount of time used in calculating multiplication equals 10 times used to calculate an addition. So that's based on the, CPU internal mechanism. Okay, yeah. So very close. Okay, very close. Yeah. Yeah. I taught computer architecture before. Okay, yeah. I taught computer architecture for graduate students many years before. Yeah. In that class, we need to study CPU, the details, how things work inside CPU. Yeah. Yeah. So based on the data there, to calculate one addition, if we use certain computer, reasonable computer, the number of time units we use to calculate one addition, 2 nanoseconds, okay? 2 nanoseconds. You know nanoseconds, right? Yeah? I hope everyone here, nano, okay? Nanoseconds. Yeah. Nanoseconds, we use NS. Nanoseconds. 1 nanoseconds equals 10 to the negative 9th second. Yeah. 1 billionth of 1 second. Okay, nanosecond. Yeah. But in CPU, to calculate one integer addition, here I'm talking about integer addition. Okay, just give you some idea. 2 nanoseconds. All right. To calculate one integer multiplication, okay, approximately 20 nanoseconds. 20 nanoseconds. Okay, approximately 10 to 1 ratio. Yeah. Yeah. So that's the base we use in our assumption, 10 to 1 ratio. Okay. Yeah. For addition, here we assume, here I do not use explicit 2 nanoseconds. Yeah, I do not use that. Yeah. I use one-time unit. Yeah. So we assume we use one-time unit to do one addition. All right. Then 10 time units we need for one multiplication. Now we need to convert, because at the end we need to combine the total time units used for the whole polynomial evaluation. We need to convert to the units of time, total number of units of the time. So let's do another step calculation. Yeah. So the total units of time, so here, I need to, erase this part. Yeah. Total number of units of time, and additions, each addition 1 unit, 1 times n units of time. Yeah. Then multiplication, we have this many multiplication. We need to multiply this number by n. Yeah. Multiply this number by n to get the number of units of time for all the multiplications. Okay? So we get 5n times n plus 1. Okay? Then add up these two subtotals to get a total number of units. So this is the total number of units. Two parts. After simplification, so we get 5n squared plus n, number of time units. So we have a number. We have a number. So we treat it as the computation cost. So this is the computation cost number. Okay? Yeah. All right. For our first algorithm, brute force algorithm. Here, let me mention our first programming project. Our first programming project, we will work on this problem. Okay? We need to do experiments calculating given polynomials using 3 algorithms. The first one, brute force algorithm, this one. Okay? Yeah. The second, third, yeah, so we will learn in the remaining part of part B. Yeah. Remaining, we will cover algorithm number 2, number 3. Yeah. So then you write your programs to do the experiments. Okay? Yeah, so that's the first program project. But given next week, not this week, you have your first quiz. Okay? This week, Friday, tomorrow. Okay? Tomorrow you will see our quiz number 1 posted. All right? Yeah, covering part A, part B. Yeah. At this point. All right, let's continue. Next question. Yeah, so we finished the brute force method. Yeah, so we're done. Yeah, brute force method, we're done. Yeah, but we're not satisfied. Yeah, remember last time, by a special example, x to the 4th, we can do better. We can do better than this brute force method, because x to the 4th, we can use one fewer multiplication to calculate x to the 4th. Yeah. There, for the whole polynomial, we have a good chance we can do better than brute force method. Okay? So next we need to look for a better algorithm. Yeah. How to reduce this number. That's our goal. Yeah. Or that's the question for our next problem. Yeah. We have several subproblems.
So for the subproblem that we just tackled, we applied the brute force method.
Yes, yeah, brute force.
And we sketched out a triangle with geometrical model.
Yeah, yeah,
That's brute force.
yeah, brute, yeah,
Every iteration.
yeah,
Every iteration up to n, and it could be like a super large.
right, yeah, yeah, brute force. Yeah, that's brute force.
Super inefficient.
Not efficient. Later you will see there is a very smart way. We can do much, much better. There is a extremely smart. Yeah, so that's why I choose this topic. Yeah, because the improvement is huge. Improvement, you cannot imagine how big is the improvement. Yeah, so we will see. Yeah, all right. Let's go to our next improvement strategy. Yeah. Next up problem, because it's harder. It's harder. Yeah. So then, to tackle that harder subproblem, right? Then, when we have relatively hard computing problem, we need to apply some suitable strategy, problem-solving strategy. Okay? Yeah, here. So let's think about what problem-solving strategy we want to apply here. Okay, all right? Yeah, first, let's look at this number. In this number, there are 2 parts, right? Yeah, there are 2 parts. The first part, addition part, right? The second part, multiplication part, okay? 5n times n plus 1. There are 2 parts. Yeah. The first part, that's the contribution from addition operation. Second part, that's the contribution from multiplication. All right. Then let me draw some simple diagram to show you the idea. Here we want to understand the issue, the problem, visually, visual understanding. All right. Let me draw a big circle to represent total amount of time used to calculate the whole polynomial. That big circle. Okay, all right. Inside that big circle, 2 parts. Addition part, multiplication part. Addition part, very small. So let me draw, small, yeah. So this little small area representing the addition part. Okay, all right. Yeah. Multiplication part. Yeah. The remaining pretty big. Remaining, all right? Yeah. All right. Based on this diagram, yeah, we use it as our visual understanding. Yeah. Our goal, we want to reduce. Yeah, our goal, we want to reduce the amount of time, right? That's our goal. Reduce this number. Reduce this whole circle. When you do the reduction from the problem-solving strategy, what is the better way? Yeah. What is the better way? Yeah. Yeah, because here, when you do the reduction, you can target two different parts. You can target the addition part. You can also target the multiplication part. Yeah. Which part you want to target? You want to put your precious investment on. Which part you want to put your precious investment? Yeah. Your resource. You want to invest your resource on one of the two parts. You need to make a decision. Okay? The first part, second part. Which part is better to put your investment? Multiplication. Because it's larger, right? You have more room for reduction, right? Yeah? Yeah. Think about if you have a chance to reduce the second part by half. That's huge, right? Yeah? Half of the second part, much, much bigger than the whole part of the first part, right? Yeah? Yeah. All right. So this understanding is summarized as a famous principle used in computer industry. It's called Amdahl's law. Amdahl's law. Okay? Yeah. Yeah. All right. Yeah. So the two parts. Yeah. Here. Yeah. Yeah. So our conclusion, we want to, yeah, because 10-to-1 ratio, you know, yeah. All right. Yeah. We have more room to improve on the multiplication part. Yeah. Yeah. So Amdahl's law tells us the basic idea of that famous Amdahl's law in computer industry. It tells us when you have limited resource to improve your current, you know, some general task, right? General task, yeah, it's talking about general task, right? You should focus on the major part. Yeah, that's the essence of this Amdahl's law, okay? Put your limited resource on major part, yeah, major part, okay? Yeah, so multiplication part, that's the major part, yeah, yeah. So it's called, you know, in Amdahl's law called most common task. You know, put your resource on the, you know, common task, most common. Okay, all right. Yeah. Conclusion. Yeah, focus more on multiplication. Yeah. Based on the Amdahl's law, we should focus on multiplications, not addition. Okay, multiplication. That's the major part. That's the most common part. All right? Yeah. All right. The strategy. Yeah. Yeah. Our next problem, we need to try our best to reduce the number of multiplications. Yeah. All right. New question. All right. How to reduce the multiplications? Yeah. Yeah. Also pretty challenging. Yeah. Well, so this, now we know our current objective clearly, but still very challenging. Yeah. So we need to do a lot of work in problem solving. Yeah. All right. So let's go to the B.3 Horner's rule. Oh, okay. Yeah. 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 Sure. Yeah. Okay. All right. Yeah. All right. Yeah. Yeah. So, All right. Yeah. Question?
So is this still the brute force?
Yeah, still brute force. Yeah. Yeah. But here, although still the brute force, but we do preparation for next algorithm. Here, yeah, because we need to, yeah. Yeah, we do, yeah, you can treat it, we do summary on the brute force method. Yeah, so this is, we can treat it, the summary for the brute force. Yeah. All right. Yeah. Yeah. Now, next, let me move to algorithm number 3. Yeah. So number 3, because in our project 1, we have 3 algorithms. You need to write the programs. Yeah. After brute force. Number 2, I will delay after number 3. So I talk about algorithm number 3 first. Yeah. After I finish that, then I talk about number 2. Okay? All right. Yeah. So this topic, B.3, title, Horner's rule, that's our algorithm number 3. Okay? Yeah. All right. Now, strategy. Yeah. So you can see in our problem sum, we keep using many different problem-solving strategies. Yeah. I hope through this class, you have good training on how to use problem-solving strategies. Okay? Yeah. Yeah. We will use many, many times. Yeah. Yeah. Try to learn the best you can. Yeah. Strategy. Yeah, study a simpler case. Yeah, we did before, right? Remember, we do experiments on simple data before. Yeah, here, same thing. Yeah. So we study a simpler case. Yeah, that's the same meaning. We do experiments using simple data. Yeah, let's do it. Right. Simpler case. Yeah. Yeah. Simpler case. Yeah. We need to choose appropriate simple case first. Appropriate. What's appropriate? Let me show you. What's the meaning? Appropriate simple case. All right. So here, here I talk about, the background understanding. Yeah. Why we use this strategy. Yeah. Not just here. This strategy is very general in our real world situations. Real world situation, many times you need to apply this strategy. Okay? Yeah. After training of this class, in real world, many different situations, you need to connect the dots. Right? So I talk about connecting the dots. Connecting to what we learn in this class. That's the dots. Right? That's our experience. So connecting the dots to what we learn in this class. Right? Discover certain property from the experiments. Yeah? Why we do simple experiments at the beginning? Because through our experiments, we try to find some special properties. We want to do observations on from these experiments. We want to summarize. We want to, observe, try to find special properties from these experiments. Yeah. All right. So it is easier to do experiment where data sizes are small. Yeah, that's obvious, right? Yeah. So when we do experiment, if we choose a polynomial with 1,000 terms, is a good idea? 1,000 terms when we do our first experiment. It's not a good idea, right? Yeah, very messy. Yeah, yeah. So that's obvious. Yeah, all right. Yeah. Then the critical property here in this experiment, we need to try to observe some critical property. Yeah. So let's do the work. Yeah. This example we choose n equals 2. N equals 2. Where a equals 2, there are 3 terms, right? So there are 3 terms. So here you may ask a question. Why we choose n equals 2? Why you do not choose n equals 0 and 1? Yeah. So there is some good reason behind it. Yeah. If you choose 0 or 1, you can get anything interesting. Okay? So we treat 0 and 1 case not meaningful. Yeah. Because too simple. Too simple, you cannot find any meaningful property from those two simple cases. Yeah. So we need to choose simple but meaningful. Yeah. So those two just appropriate. Yeah.
They were more things like 3 times the charm.
Yeah. 3 what?
3 times the charm, that same rate.
Yeah.
Like instead of just 2 instances that we use as a solution.
Right.
So we can go like it, then we use the charm.
Yes. Right. 3. Yeah. So here, yeah, the issue is because we want to explore the relationship between the terms, among the terms. If you have 1 term or 2 terms, you do not have many terms to be considered, right? There's no room to explore the relationship. So 3, yeah, we have enough many terms so we can explore the relationship among the terms, right? Yeah, that's the meaning. Okay? Yeah. Too little, no room, nothing we can do, right? Too few, yeah, the number of terms, nothing we can do. Yeah, we just stare at it, yeah, do nothing, right? So if you have 3 terms, yeah, you have some room to work, yeah. So you can do some meaningful work. Yeah. Otherwise, no room to do the manipulation, right? No room to do manipulation. All right, let's work on this 3-term polynomial. All right, yeah, let's look at the last 2 terms and try to see some interesting property on last 2 terms. Yeah. So there is a important property if you look at last 2 terms, common factor. These 2 terms, they have a common factor property. Okay? Yeah. That's useful. Yeah. But if you look at 1 term, can you see common property? No. If you look at 2 terms, can you see common property? No, right? Yeah. So for that reason, we need to have a little more terms. Then we can talk about common factor. Otherwise, the common factor property is hidden, right? Yeah. So you cannot reveal the common factor property. When we choose 3 terms, then we can reveal the common factor property. That's important, right? Yeah. The next step, when you see the common factor property, next, you can do some manipulation related to the common factor property. Yeah. Factorization, right? When you see common factor, the obvious operation is the factorization. Yeah. Yeah. All right. Yeah. So let's do the factorization operation on the simple polynomial. Yeah. All right. All right. The last 2 terms before factorization. Yeah, that's before factorization. Then after factorization, we factor the common factor x out. Yeah. Same, right? Yeah. Equal, same. Yeah. So the same value, these 2 expressions, left-hand side, right-hand side of this equality has the same value, but they have different forms, right? The forms are different. Yeah. So here, that's a typical way we do in problem solving. We do transformation. So this is the transformation work we do in problem solving. We change the form, but we do not change the content. Content the same. Okay? The value, internal, the final value, we do not change that. But we change its form. Yeah. The form change, it matters. Yeah. It matters, the form change. Because after the form change, let us count the number of multiplications again and see if we have some different result. Yeah. All right. Before factorization, how many multiplications? Can you count quickly? Count quickly. Number of multiplications before factorization. 1 contribution, 2 contribution, adding together 3 total multiplications. Yeah. All right. After factorization, let us count the number of multiplications we need for the second form. Yeah. All right. X times parenthesis. There is 1 here, right? Yeah. 1 multiplication between x and that pair of parentheses. Another multiplication between A2 and x, right? That's all we need. We only need these 2 multiplications. So you get 2 multiplications. Is that a reduction? You get a reduction, right? You reduce from 3 to 2. Yeah. So you get 1 number reduction. Yeah. On this simple polynomial, you can save 1 multiplication. That's the progress. That's the progress. Yeah. Encouraging, right? Yeah. That's encouraging. We are doing something positive, right? Positive. Yeah. All right. Yeah. So our conclusion, by factorization. So why we can get this improvement? Because of this important operation, factorization. Okay, all right. So our gain, the gain result from 3 to 2. Yeah. Nice reduction. Yeah. Although not much, yeah, but quite encouraging. Quite encouraging. Yeah. All right, yeah. Summary. Yeah. We changed the order of operations. Do you remember last time I talked about order of operations? When you change the order of the operations, you have a chance to get different results. That's what I said last time, right? Yeah. When you change the orders of the operations, you have good chance to get different results. Yeah. I didn't say better result or worse result. Yeah. Different results. Yeah. At least some hope for better, right? Some hope for better. Yeah. Here. So we changed the order of operations by factorization. Yeah. So here, because last time when I mentioned that statement, I didn't say how to change the order, right? Yeah. So you may wonder how to change the order. Now you know it, right? You know we can change order by factorization. See? Yeah. Here. Yeah. Give you the specific way to change the order. Yeah. All right. That results in better. Yeah. Now we see the result. It's better. Okay. Better efficiency. Yeah. All right. Yeah. Yeah. So it's a encouraging intermediate result. Yeah. Yeah. We get encouraging intermediate result. Let's keep going along this direction. Yeah. Let's explore this idea. Yeah. Or let's generalize this idea to our general case, right? Yeah, because general case, our n is a general number. Yeah. Right? Yeah. So we need to get to our destination. That's our destination. Yeah. All right. Yeah. Question: how can we generalize this idea to general n? Yeah. We have to do that. Yeah. That's our goal. Yeah. All right. Next. Now we need to do the generalization. The goal: reduce the number of multiplications. Yeah. There, now we have better idea by factorization. Yeah. Yeah. Here, because here our understanding is much better by factorization. Right? Yeah. But another question is how, right? How do you do the factorization? Yeah. Another important question. Yeah. So we need to address this question here. How to use the factorization in a smart way. Yeah. All right? Yeah. That's our current objective. Yeah. All right. But we only did one simple example. In that one example, we feel still not enough experience collected from that simple example. So we need to, let's try another simple example so that we can collect a little more useful experience. Yeah. So let's do one more. N equals 3. Yeah. Yeah. Because sometimes when we see we haven't collected enough information to make our final conclusion, we need to do a little more experiments. Yeah. Here, let's do one more experiment. N equals 3. Yeah. In this case, what should we do? Yeah. Yeah. Still factorization, because we want to answer how to do the factorization. Yeah. Yeah. So in this N equals 3 case, we want to answer this question: how to do the factorization in the right way so that we can generalize our final step. We want to generalize this factorization technique to cover the general case. General case. Yeah, that's our goal. Yeah. So that's why we need this example. Okay? All right. Let's do it. The key to the success. So far, so we enjoy some partial success. All right? Yeah. So it's not the final success. Yeah.
There's more to this than just factorization, right?
Yeah. Yeah.
You can't just factor stuff out. There's also other sources of inefficiency that you've got to figure out where to attack. You can't just factor or brute force it, got to be elements and stuff.
Yeah. Right. So here, that's the reason it's not brute force. Yeah, because we apply factorization technique.
Nobody has no time for that sometimes.
Yeah, in my project, I will give you that description. Yeah, in a project, I will set up the problem. Yeah. So you will see. I try to make it easier for you to do the work. All right? Yeah. So key to the success is factorization. Yeah. So our decision. So now we want to take advantage of the factorization technique. Right? Yeah. That's our decision. Yeah. The question, how? We need more information. To see how, we need more information. All right. So now, let's do the factorization. But when we do the factorization, we know factorization is some nice thing. Yeah. So that's the reason we can do better. Yeah. If it is a positive thing to our success, factorization is a positive thing to our success. Then, when we apply factorization, then we should make this factorization cover as many terms as possible, right? Yeah. Cover many terms as possible. Then we can get more save, right? Yeah. We want to save more. So in order to save more, we want to cover more terms. Is that a reasonable deduction? Right? Yeah, reasonable. Yeah. All right. Let's cover more. The maximum number of terms we can cover, the 3 terms we can cover. 3 terms. Yeah. That's the maximum we can cover. Yeah. Because we cannot cover all 4 terms. So only 3 terms. Yeah. 3 terms, so we do our first factorization. Okay? Yeah? All right. Then after our first factorization, can you still do more factorization? Yeah. Because every time when you do one factorization, you can save certain number of multiplications, right? Yeah. If you do more factorizations, then you can save more multiplications, right? Yeah. So that's our understanding. Based on our understanding, that's the natural flow of our understanding. Okay? So you need to have your logic, understanding some reasonable logic. Okay? So next, then in the remaining expressions, can you do more factorization? No, because if you look at the last two terms, inside the parenthesis part, they have common factor, right? Yeah. So you can do another round factorization, second round factorization. How about that? Okay. So let's apply the second round factorization inside the parenthesis. Okay. All right. All right. Yeah. Yeah. So then, in that way, you can see, yeah, you can get the maximum number of factorization, right? Yeah. Until you cannot, right? Yeah. Because after second round, then no more. Yeah. Because we couldn't. Yeah. We have to stop. Yeah. After 2 rounds factorization, we have to stop. Yeah. Yeah. All right. After we stop, can you do the counting? Can you do the counting? All right. Now we want to see how much is the improvement. Yeah. We want to see that. Yeah. But before we do that, before we want to see that number, important progress number, yeah, let's do the counting before factorization. Still, we need to do comparison. Yeah. Before factorization, this term, 1 contribution to the total number of multiplications. This term, 2 multiplications to the total. Yeah. Last term, 3 multiplication to the total. Okay? Adding together the total number of multiplications, 6. 6. Before factorization, we need a total 6 multiplications to calculate this polynomial. Now, after 2 rounds of factorizations, let's do the counting. First multiplication occurs between x and the first pair of parentheses, right? 1. Yeah. Second multiplication occurs between this x and the internal pair of parentheses, right? Yeah. Second. Third multiplication between x3 and x3. Total, now we add, equals 3. Okay. Yeah. That's the improvement, right? That's the improvement. Okay? Yeah. Is it big? Yeah. Is it big progress? Yeah. Good progress? Yeah. 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 So now, after this experiment, we collect more information. So we feel we can make the final conclusion. Yeah. Final conclusion. Yeah. For the general case. Yeah. For general case, what should we do for the general case? Yeah. So let me show you. Yeah. The general case. When we go to the general case, we need to generalize this idea. Okay? And we know the key to the success of this idea, that's the factorization. And we have experience. The more we use factorization, the better result we can get, right? Yeah. That's our experience. Yeah. So then we want to push forward. So this idea, yeah, this thinking, yeah, another step forward. Yeah. How do we push this idea forward? We want to apply certain method here. In our situation, this certain method is the factorization method. We apply factorization method as much as possible. This is how we push it forward for the general case. General case, the way you do it, yeah, apply factorization as many rounds as possible. No, not that simple. Yeah, not that simple. Yeah.
You're trying to reduce the number of multiplications.
Yeah.
More x to go, more multiplicative operations you have to run. So that means that that's the current algorithm.
Yeah. Right, yeah. Oh, yeah. Actually, yeah, right. Actually, you pretty much get there. Yeah, you pretty much get there. Yeah. So that's the generalization. Yeah, but yeah, let me introduce. Yeah, because based on this idea, there is a important algorithm, type of algorithm. We call the greedy algorithm. Yeah. So here, let me talk about this greedy algorithm. In computer algorithms, this idea also very useful. Yeah. So let me talk about the greedy algorithm. Yeah. Because this, as much as possible, corresponds to this greedy word. Yeah. How do you apply some useful thing as much as possible? Yeah. So here, people use some negative word, greedy. Yeah, but here, we treat it as a positive thing. We apply some useful property as much as we can. That's positive. Yeah. All right. Idea. Yeah. Now we need to push it to the general case. Right. The strategy for generalization. Do factorization as much as we can. That is the greedy idea. Okay. All right. So therefore, the greedy algorithms, we apply some property as much as we can at each step. So here, let me give you the complete description of the greedy algorithm. Yeah. As much as we can, but at each step. I emphasize this each step. Yeah. Because this each step, that is the local way. Local way. Not global way. No, each step local, not a global. Globally. Okay? Now, the reason why locally, not globally, because it's easy to do it locally. Yeah? When you make a local decision, is it easy? Yeah, it's easy. Yeah. When you make a local decision, because you don't need to consider many other things globally. You only need to look at a small portion of the whole thing. Yeah, that's easy. Yeah. If you want to do it globally, then too hard because too many considerations everywhere. Yeah, extremely hard. We cannot make it. Yeah. So what we can do? Making this kind of local decision. Local decision. Yeah, we can do it. That's the reason the greedy algorithm is some kind of easy algorithm, easy way to solve problems. All right? All right. Yeah, so I emphasize that. Because it is some easy way, then there is some potential problem. The greedy algorithm has some potential problem. Yeah. Because it is easy. Yeah. You didn't do it globally. Yeah. You may have some potential problem. The potential problem. So the greedy algorithm is just locally optimal, but easy to achieve, but it may not be globally optimal. Right? Yeah. It may not be globally. That's the potential problem. Right? Globally, so it may not be optimal. Yeah. If we say optimal, we mean global optimal. Okay? Yeah. If we say some algorithm is optimal, then overall it is optimal. Yeah. Considering all the possibilities, it's optimal. Yeah. All right. Because to get a global optimal solution, extremely hard. Yeah. Extremely hard. Yeah. Most of the time, we cannot make it. Yeah. For hard problems, most of the time, we cannot get a globally optimal solution. Okay? Yeah. So that's the reality. That we try to get the best we can, but because this optimal thing, that is a big requirement, hard to achieve. Extremely hard to achieve. Yeah. So our attitude, we want to get close to optimal. So then we will be very satisfied. If some algorithm is close to optimal, not absolute optimal, near optimal, then we will be very happy. Very happy. Yeah. All right. Now, the generalization here. Yeah. Yeah. This time we apply the greedy algorithm. We want to do factorization as much as we can. Okay. All right? Yeah. So you treat this as brute force?
I mean, it's got like a similar energy in brute force, considering that brute force.
Don't say energy. Yeah. So here, because your word, you use this energy probably regarding the complexity, right? Because it's simple. It's not complicated. Yeah. No. So here, yeah, actually you raise an interesting question. Actually, the value of some special technique, it's not at the complexity. It's at its how smart it is. Something very smart could be very simple. Something very simple but extremely smart. All right? So don't use, so because people tend to treat some complex thing sophisticated, then it's advanced. Yeah, many people tend to think in that. Actually, it's not that. Sometimes simple methods could be better than sophisticated methods. Right? Yeah? Right? You see, our computer's very powerful, right? That's based on 0, 1, 2 bits. Is that simple? Yeah. Simpler than 10-digit system, right? Yeah. But the computers like the binary system. If you compare which one is more sophisticated, then digital system is more sophisticated than binary system, right? Yeah. But in reality, binary system is better in computation than digital system. Okay? Yeah. So yeah, but that's a good point. Okay? Yeah. So we talk about how smart is this algorithm? The idea. Yeah. All right? Think about that. Yeah. So not complexity, not sophistication, okay? Not that. All right? So this is not brute force. Do you agree? This is not brute force method. Brute force method, that means people without any experience, they can do it. People without any experience, training, yeah, people just with some basic experience in the real, they can do it. That's brute force, okay? Yeah, without any high-level training, okay? Yeah. But think about, if people without training, how do you know? You should use the Horner's. This is Horner's rule, okay? Horner's rule. How do you know? You can use Horner's rule, right? Yeah. All right? Yeah. Now, this is our generalization. We apply factorization as many rounds as possible. Is this way the best way to apply factorization? Yeah. That's the best possible way to apply factorization technique here. Yeah. Because my understanding of the brute force method, if you apply any special technique, then we cannot treat it as brute force. Okay? Special technique, yeah, then it's not brute force. Yeah. Because that special technique plays extremely important role on your final result. So here, yeah, the Horner's rule. All right? Yeah. Now do the counting. Now, at the end, we need to do the counting. We count. Yeah, let me look at how much time. No, not much time. Yeah. How many multiplications do we need based on this formula? The special form, this formula. How many? Counting? Yeah, yeah. All right. See this? We see this ellipsis again. We see this ellipsis again. Does that cause some problem? Disturbing? Causing some problem? When that happens, Connecting the dots. What did we learn before? Connecting the dots. We have learned some effective method in this situation. Recall, yeah, you need to connect the dots. Counting by reference. Remember, I talked about counting by reference technique last time. Let us establish between multiplication object and another suitable reference. We need to choose suitable reference object. Establish one-to-one correspondence, then we can do the counting. All right. Here, the suitable one-to-one correspondence. The first multiplication is here. Can we associate with the subscript of this A1? Coefficient A1. Association. One-to-one association. All right? Yeah. Then, the second multiplication, this is the second multiplication. Can we associate with this subscript of A2 coefficient? And one-to-one, yeah, one-to-one. All right? Yeah. Then, ellipsis, yeah. Now, because based on this rule, so you can skip many terms. Then this multiplication, this one, can you associate with the subscript of its right-hand side nearest coefficient? Yeah? Right? We do this kind of association. Yeah. Then the last one, this multiplication, can we associate with, that subscript? After this kind of one-to-one correspondence, now, when you do the counting, you just count the number of subscripts, right? Yeah. Yeah. Now, yeah, we do not count the multiplication directly because we have reference objects, one-to-one correspondence reference object. So we just count number of, all right, yeah. So let me finish quickly. Count the number of subscripts. That's easy, right? You can see it. That number is n. So this number is n. All right? Yeah. Number is n. Okay? Yeah. That's so-called Horner's rule. Yeah. That's our third algorithm in your project one. First one, third one, then next class, second one. I'll give you a second one. All right? Yeah. Then you can do your first programming project after next class. Yeah. All right. Yeah. So check the canvas. So you will see the quiz number 1 early in the morning. Tomorrow morning. All right? Yeah. Due next Sunday. End of next Sunday. So you have a lot of time because you need to use it to do study. Okay? I'll give you time to do study. Yeah. So take time to do study. Watch the videos, then do some study. Yeah. So you have more than 1 week to complete. Yeah. Plenty of time.